Hi, my name is Jonathan Dodge, Principal Applications Engineer at United Silicon Carbide. And in this video we'll take a look at a new topology in FET-Jet Calculator version 2, which is the H-Bridge topology in AC-DC section of converters. So let's see what we have here. So it's an H-Bridge, and you can control it different ways. So we have a few choices here. Under modulation, you can choose unipolar with 2 carriers, and so you can see the control chart on the left of the circuit diagram. We have 2 sets of carrier waveforms and a single control waveform, and it is somewhat color coded to match the switch positions in the little schematic here, and then also the losses per FET in the chart on the right. So that's Unipolar TwoCarrier. We'll take a little closer look at each of these in a minute. There's Unipolar TwoControl single carrier. So here we have 2 control signals and a single carrier waveform. And again, they're color coded. And then the last one is bipolar. This one is basically the same as same kind of control as in a 2-level voltage source inverter, single phase of a 2-level BSI. Okay, so let's take a look at some simulation waveforms. So PSIM is a program that's very easy to use. So we draw a little schematic with an RL load, HBridge, and run it. So in the results, we have on the top screen the red. This is the load current switching at a low frequency, so we can see the switching events a little more clearly. The blue, this is the modulating, or in other words, the control signal. Okay, and I've scaled the load current so it's about the same amplitude, so you can see a little bit of phase shift from the resistive inductive nature of the load. And then the next screen down, we have again the control signal being compared against the triangular carrier waveform, and the resulting current through Q1, the upper left FET. So you can see forward and reverse current flowing. So this is bipolar. What do we mean by bipolar? So we'll take a look at the voltage across the load, and you'll see it is plus 400 minus 400. Well, 400 is our DC link voltage. So bipolar means we have, with each switching cycle, a transition from plus to minus 400 volts. So that's why it's called bipolar pulse width modulation. Okay, so now let's take a look at unipolar TwoControl. So again, the same H-bridge, same RL load, but a little bit different way of controlling it. So again, we have the same control signal and scaled load current, and then we have 2 control signals being compared against a single triangle wave, and the resulting currents. This time they're shown in Q1 and Q3 in the 2 different legs here. So these are the 2 high side switches. Okay, and this is unipolar. So if we take a look at the voltage across the load, you'll see now it switches at any given switching cycle only 400 volts, from 0 to plus 400 or from 0 to minus 400. So hence the term unipolar switching. Okay, and then the last one, Unipolar TwoCarrier. Run that. Okay. Same two signals in the top screen as before, scaled load current and the control signal. Now we have a single control signal compared against two triangular waves, and quite different waveforms now, showing the current waveform in each of the four FETs, so it's easier to understand. So we have current in Q1, and because it's a RL load, a little bit lagging power factor, there is some negative current. Otherwise, with a unity power factor, it would be just all forward current. Same for Q3, and then for Q2 and Q4, they remain on for half the line cycle, and so you'll see their current is just the envelope of the others during that half a line cycle, and then otherwise they have some switching current going on. So going back to the calculator, we'll see that for bipolar and for unipolar to control, the switching loss is the same for each switch position, so there's no label Q1 through Q4 on these. It's all the same switching loss. In fact, those two topologies, interestingly enough, produce the same loss, but quite different waveform. If we look closely, the load frequency has been doubled. So in other words, the frequency seen across the output of each leg is twice that of the other modulation methods. So this is a real advantage, because without any additional switching loss, you can double your switching frequency at the load. And then there's Unipolar TwoCarrier, which in this case the loading is different for the high side versus the low side, and therefore split up between Q1, Q3 versus Q2 and Q4 in this case. So hopefully that clears things up a little bit with the H-Bridge single phase inverter, and I appreciate any feedback. Thanks for watching.